Hi, everyone. Welcome to our video lecture for Math 60. And is that big enough for all to see? I think I'll zoom in a little bit. I just have to do it that way. That's a little better. Okay. Our video lecture for sections 3.3 and maybe some of 3.4. We'll see where we get. The nice thing about 3.3 is actually we've covered a lot of it already. Because 3.3 is prime factorization. And I previewed that last week on purpose because I think prime factorization is the most helpful way to find a greatest common denominator. We're going to basically, it's going to end up kind of being a review and from last week and a few more ideas. So let's start with talking about what are prime numbers. Well, first of all, we're working in the world of integers. So prime numbers are always going to be integers. A prime number is a positive integer that is only divisible by itself and the number 1. Now, technically, when I say divisible, you can always divide a number. You just might not get a whole number as a result. So when I say divisible, that means you can divide it and you end up with a whole number. So let's start listing them. We're just going to list our numbers, but in particular, as I list them, prime numbers are the building blocks of all numbers using multiplication. I should say all integers, not all numbers. So we're just going to start listing out our numbers and we're going to see when can I build it from prime numbers and when can I not. So number 1, that's our first number. This is not a prime. Mostly because if you made the number 1 a prime, your world would not be very interesting. 2, right? The number 2 is divisible only by itself and the number 1. So 2 actually is a prime. Well, 3, I can't divide 3 by 2, so 3 is also a prime. But 4 is 2 times 2, so 4 is not a prime. 5, yeah, I got to get 5 on its own, but 6 is 2 times 3, so again, it's not a prime. So our prime numbers, starting with 2, I'm going to list them vertically. And all the other numbers I can list using some of the multiplication. 8 is 2 times 2 times 2. 9 is 3 times 3. 10 is 2 times 5. I'll go ahead and put it here. But 11, all right, I have to put over here because I can't get 11 by multiplying any other numbers. 12, that's not a problem. I can put it here. 12 is 4 times 3, but if I want to write it using only primes, it's 2 times 2 times 3. This is a different version of that grid I showed this class last time, where I started with all the numbers from 1 to 100, and then I chopped out the ones that were multiples. And here I'm building it up, but it's the same idea. The other way I like to think about prime numbers is that they're line numbers. And again, if I were building math, I would call them line numbers in general. Because if you think of numbers as being these little squares, prime numbers you can only write in a straight line. Again, number 1, that's a square number, so that's definitely not a prime number. There's 3. Now, 4 I can write as a line, but 4 I can also write as a square. 5 I can only write as a line. If I tried to make this into a rectangle, I would end up with 3 and 2, and that's not a perfect rectangle. All right, and then 6 I can write as a rectangle. So we've got line numbers and we've got rectangle numbers. And square numbers actually are part of our rectangle numbers. And that also makes sense why 1 is not prime, because 1 is a square number. But mathematicians have a different name for rectangle numbers, and that is composite numbers. Composite numbers are numbers that are not prime. All right, so when we think about finding that greatest common denominator, the greatest common denominator is the largest number that divides all the other numbers. I really should be more specific. Greatest common denominator of 2 or more numbers, but the GCD. And we found that using primes. In fact, using something called the prime factorization. The prime factorization is exactly what I have up here. It's where I take a number and I write it as a multiple of only primes. So the prime factorization of 8 is 2 times 2 times 2. The prime factorization of 12 is 2 times 2 times 3. The prime factorization of 10 is 2 times 5. And the prime factorization of 7 is just 7, because 7 itself is prime. So even primes have a prime factorization, it's just the number itself. Finding all of the primes that make a number make division a lot easier. And so that's why it's helpful to be able to do the operation of finding a prime factorization. Let's talk about how to find a prime factorization. One is just maybe you already prime factorization of a number. There we go. Maybe you already know how to factor the number. Right? That's certainly possible. What's the prime factorization of 15? 5 times 3, right? We didn't need any kind of algorithm to get us there because Jesse knows that 15 is 5 times 3. 5 times 3 are both prime numbers. If you don't know, we're gonna use a numerical representation idea, and we're just gonna try dividing by numbers. And we're gonna do this in a real systematic way. Start with the number 2. And in fact, that only makes sense if the number is even. Because if it's not even, there's no point in dividing by 2. If 2 doesn't work, try, what would be a good number to try after 2? Yeah, try 3. If 3 doesn't work, try, what would be a good number to try after 3? Why not 4? Yeah, because if I could divide it by 4, I could have divided it by 2. And in fact, if you notice what we're trying is we're trying all the prime numbers. Keep trying prime numbers. Anyway, we're trying to find the prime factorization, so prime numbers make sense. So let's do an example. Let me think of a nice big number. Okay, here's a nice big number. 10,010. Any idea for a number that we could try? 2, because it's even. Yeah, okay. So this is even. So let's try 2. And here's how I'm going to suggest you keep this organized. The book uses this division sort of thing where you put 10,010 and 2 like this. I'm gonna say let's not do that because we want to keep track of things. So 10,010 should be 2 times, and then how do you figure it out? Well, you grab your calculator and you do 10,010 and you divide it by 2 and you get 5,005. You don't have to prime factor without a calculator. Calculators are super useful for this. $5,005. Well, if that's prime, we're done. But if it's not prime, we got to keep trying. So what's a number we could try after 2? We could try 2 again. Would 2 again make sense? No, because this part's not even anymore. So let's try 3, just in case. So we're gonna do 5,005 divided by 3. And that's 1668.333. So it doesn't divide by 3. Okay, 3 didn't work, that's okay. So now let's try 5, because that's the next one. Also, as Jesse noticed, any number that ends in a 5 is divisible by 5. So that would be a good idea anyway. So the reason I want you to write it vertically is so you can keep track of all these primes as you're factoring them out. The 2 come straight down, and then we split by 5. And we get 1,001. And if 1,001 is prime, then we're done. But I don't know if 1,001 is prime. So we could try 2 again, doesn't make sense, we already know that. We could try 5 again, but again, that wouldn't work because it doesn't end in a 5. So let's try another number. How about, Jillian, what number should we try? Let's try 7. We get 1001 divided by 7. And it does work. So I have the 2, which comes down, the 5, which comes down, and then the 7, which multiplies by 143. Now we're kind of in a rhythm. No point in trying 8 or 9 because neither of those numbers is prime. Or 10 for a couple of reasons. One, it doesn't end in a 0, so it's definitely not divisible by 10 anymore. So let's try 11. And the way I built it, I think this is going to work. It's going to be ending up 11 times 13. Now, if 13 is prime, we're done. Do we know if 13 is prime? It is, yeah, 13 is prime. So we're done. And we have written 10,010 as a product of only prime numbers. That's what it means to say the prime numbers are the building blocks of any number. Your number is either prime or you can build it by multiplying primes. Okay. Any questions about that process? So I strongly recommend that, especially as you're developing this skill, that you do it vertically because it's really easy to forget when you peel off those primes. It's easy to forget them. But if we're going to have equal signs, then they need to be equal all the way down. Let's do another example. All right, I'm going to write this example on down. Find the prime factorization of 936. I'm going to pause the video and everybody work on it a little bit. All right. So I just checked with some of the folks here, and one of the interesting things about this is there's a lot of different ways to do it. I think Jillian had an intuition that this number is probably divisible by 3. So you started with 3 and it worked. Great. There's not a wrong way to get to the right answer in math. And that's something to keep in mind. There's no wrong way to get to the right answer in math. There are ways that maybe are more efficient or a systematic way that can benefit you when things get more challenging. So that's what I'm teaching here. But if you get to the right answer, you get to the right answer. So the first thing I'm going to do is I'm going to say, what's the smallest prime I could try, which is 2. And if it's even, it works. And this one's even. So 936 does equal 2 times, what's that going to be? 4 what? 68? 468. And as long as 2 still works, I'm going to continue using 2. And the reason that helps is I think Jose noticed this number is divisible by 4, which is great, but 4 is not a prime, right? So that's not going to get us all the way down into the prime building blocks. So I'm just going to keep dividing by 2 as long as I can. And that one I can do in my head. That's 234, right? No.
Yeah, it is.
Yeah?
Yeah.
Oh, good. All right. Oh, which is still even. So I can divide it by 2 again. And now do you see one reason why it's really helpful to do it vertically? To keep track of all of these 2's that are peeling off of it. That's 117. Oops, I lost track of it. Sorry. See? Try again. 2 times 2 times 2 times 117. All right, no point in trying to divide by 2 again, because that number is odd. So I'll divide by the next prime, which is 3. And I'm gonna get 39, I think.
Yeah.
Yeah, 39. Okay. Now here you might find yourself right, you might not look at this and recognize that 39 is divisible by 3. And that's okay. You can try your other primes. 5 obviously wouldn't work. You could try 7 and it wouldn't work. You could try 11 and it wouldn't work. But if you try 13, it would work, because 39 is 13 times 3. And just to keep things in order, we usually list our primes from smallest to largest, because that's the way we usually go about factoring by primes. So 936 is 2 times 2 times 2 times 3 times 3 times 13. And to have it a little more compact, we usually use exponential notation. 2 times 2 times 2 times 3 times 3 times 13. How do you know if you got it right? Just check it. Yeah. Grab your calculator and do the 2 times 2 times 2 times 3 times 3 times 13. You're going to get back to 936. And if I had missed the fact that I forgot that 2 right there, it probably would have caught it when I had checked my work. All right, I have a question for you. What's the greatest common divisor of 10,010 and 936? Close? That's part of it. That's also part of it. I mean, those pieces together make it. So 10,010 we saw was 2 times 5 times 7 times 11 times 13. And 936 was 2 times 2 times 2 times 3 times 3 times 13. And if it's a common divisor, it should show up in both. 13 shows up in both, and so does one of the 2's. So 2 times 13, oops, 2 times 13 together are the factors that show up in both. So the greatest common divisor is 26.
You have to multiply both.
You multiply it out. Yeah, you find all the primes that they share in common, and you multiply those primes together to get the greatest common divisor. And I certainly would not have wanted to try to find the GCD of these two numbers without first getting those primes personally. A lot of math is the systematic process can make things a little bit slower, but the effectiveness of it in the end makes it faster. Yeah, Jesse.
To put that in like different terms, like, how we have to multiply them together.
This part here.
Yeah, what would be another way to like?
So I know that 2 times 13 can divide both 10,010 and also 936. So 2 is a divisor of both, and so is 13, but they're not the greatest divisors. How do we get the greatest divisor? By multiplying those 2 together. Yeah. Yeah. All right, one more, and then we'll move on to our next section. Let's try, and we'll do this one together. Let's look at the prime factorization. Of 127. Let's see. Does dividing 127 by 2 work?
No.
No, because it's not even. How about 3? It seems like it, because 27 is divisible by 3, but that 100's gonna mess things up, actually. It's like 42.3, I think. Right? Yeah, okay, that doesn't work. Is 5 gonna work? No, doesn't end in 5. Is 7 gonna work? You just check with your calculator.
No.
No, 7 doesn't work. How about 11? That's not gonna work. Okay. 13?
No.
No. How long do I have to do this? 17? No. 19?
No.
No. How much longer do you think I need to go to check primes? Would I have to go past 127? Definitely not, right? Because if I'm checking numbers that are bigger, then it's not going to divide. Jesse?
One question. All those numbers are prime.
Yes.
That'd be a prime number.
Well, there's more prime number. It could, I haven't checked 23 yet. I haven't checked 29 or 31 or 37 or 39 or 41 or 43. Right. Yeah. So so far, none of these work. But my question, which is getting to Jesse's point, is how many numbers, how many prime numbers do I have to check before I say, well, it's got to be prime? Can we agree I don't need to check any numbers bigger than 127? Because that obviously wouldn't divide. Can I find because that's still a lot of numbers, right? Even with the primes, that's like, I don't know, something like 30 prime numbers I'd have to check. And 127 is not a very big number. Can I lower that limit? Can I stop even sooner? Probably. Give me an argument for why. Would I have to check? So I know that I think 97 is a prime number. Would I have to try 97? 127 divided by 97? Why not, Jesse?
Because it doesn't do it.
Yeah, right. I mean, I couldn't even multiply it by 2. I would be out of range. What about 79? 79 is a prime number. Do I have to check 79? Because again, 79, even if I multiplied it by 2, it wouldn't work. So really, I shouldn't have to check any prime that's bigger than half of that number. Because, right? I mean, if I can't multiply it by 2, then I definitely couldn't multiply by 3. Let's go a little bit deeper and let's actually figure out what these numbers are and see if we have a pattern. Okay, so I'm going to take 127 here and I'm going to divide it by the various different numbers, and we're going to actually write down what we find out. This one is 63.5. This one is 42.333. This one is 25.2. I can't do the 7 in my head.
18.14.
Thank you. 18.14, etc. The 11 is gonna be 11.5555, I think.
5454.
Yeah, I was close. How about 13?
9.76923076.
Okay, 9.76. Here's the key. As soon as I get to 11, these numbers here on the right side start getting smaller again. Right? 11 times 11 is 121. This 13, this numbers, these are going to get smaller and smaller and smaller. If I do 17, it's 7.47. So my cutoff is actually, for this one, it's 11. Because if I can't multiply 11 by a prime, then going bigger is not going to help either because I'm going back this way. And the key is, this is just a little thing to remember when you're checking primes. You can stop checking after the square root of the number. Square root of 127 is about 11.26. Right, and I can stop checking after 11. Which is kind of nice, because otherwise you'd take a big prime number that's checking an awful lot. So that's just a little tip. I mean, you can always go up all the way to 127. You could even go up halfway, right? Because then the 2 doesn't work. But you can actually stop after the square root of that number. And it actually has exactly to do with the idea of line numbers. All right, if this is 127 as a line, and I'm trying all my different primes, I'm trying it in 2 levels, which doesn't work. And I'm trying it in 3 levels, which doesn't work. And 4 levels and 5 levels, and eventually I try it in 11 levels. And if it doesn't work when it's almost square, then the next one in 17 levels or 13 levels or whatever is also not going to work. Because I'm basically twisting my rectangle back to look like this one. That's useful, but honestly, that was mostly just for fun. Okay. 2 other cool facts. We're not going to go into this, but just because I think prime numbers are cool. There are an infinite number of prime numbers. There's no such thing as a finite list of the prime numbers. You got to go forever and ever and ever. You can always find another one, but no one knows if there are an infinite number of what are called twin primes. Twin primes are primes that are only 2 apart. 3 and 5, 11 and 13, 17 and 19, 41 and 43. Nobody's ever proven that there is an infinite or that there isn't an infinite number of twin primes. That's an open question in mathematics. And yet it's so easy to state. That definitely will not be on any tests. But it's kind of cool. I mean, no matter what number your math course is, there's always interesting questions. Let's move on to section 3.4, which is equivalent fractions. This is an extremely useful, a very, very useful section. One of the most useful sections you're going to learn in this class. Any number, whether it's an integer or a rational number, can be written lots of different ways. In fact, an infinite number of different ways. Just by changing the denominator. And I'll give you as an example, the fraction 1/2. If I change the denominator, I could write it as 2/4, or 3/6, or 4/8, or -1 over -2. These are all the exact same number, and I get it just by picking a different denominator and then forcing the numerator to match. And if I were to show you as a pi, there's 1/2. Let me shade in the part. There's 1/2. There's 2/4. How do we do 3/6? Like this. There's 3/6. Here's 4/8. 1, 2, 3, 4. And I'm not going to try to do the -1 over -2 because I don't know what a negative pi looks like. The reason this is so useful is when we're working with fractions, we often have fractions that have different denominators, and that limits the type of operations we can do. So if we can write our fractions that have the same denominators, that opens up a world of our operations. In particular, you can only add or subtract fractions if they have the same denominator. Denominator, by the way, means bottom. They have the same bottom of the fraction. And we come back to this in a later section. But if I tried to add 1/2 and I don't want to do that one. Let's just do 1/2 and 1/3. They don't have the same denominator, so I can't add them. So 1/2 equals 3/6, and 1/3 equals 2/6. And now I can add them because they have the same denominator, and I get 5/6, which if we do our pi should make sense. There's the 1, the 2, the 3, the 4, the 5, and forgive the bad slicing of the pie. So being able to find an equivalent fraction is an extremely useful tool, one of the most, as soon as we leave the world of integers. There's well, I'm not quite there yet. So as an aside, by the way, the number 1 as an equivalent fraction is used all the time. And you've already been using it a lot. If I have 13x equals 39, how did we solve 13x equals 39?
You're right.
We divide 39, we divide both sides by 13. And I said the 13s on the left cancel, which they do. And the reason is because it's 13 over 13 times x. And 13 over 13 is an equivalent fraction for the number 1. And so the 13 over the 13 is like a 1 times x. And we use that all the time. Anytime you are solving an equation that involves multiplication or division, at some point you use the fact that the number 1 can be written as an equivalent fraction, any number divided by itself, except for 0. Okay. Fractions in lowest terms. It's important to be able to do this. This is kind of the opposite of the usefulness. Like, if I say I have 2/6, is that fraction in lowest terms? No, but who cares? It's still 2/6, right? It's 2 out of 6. It's that piece of the pie. So in my mathematical mind, I generally don't care if a fraction is given in lowest terms or not. It's not in lowest terms, and there's a specific reason. Because there is a prime in the top and in the bottom that could cancel. That's really what it means to say you're not in lowest terms, is you have a prime that's shared in the top and the bottom. Any number, but ultimately the prime. 2 over 6 is 2 divided by 2 times 3. And now we can see there's a prime that's in the top and the bottom that could cancel. And to be really clear, let's write it as a 2 times 1 so we don't lose track. So the 2's cancel and we have a 1/3. So that fraction is in lowest terms. Let me just do another example. Let's look at 24 over 144. I notice both the top and bottom are even, so I definitely know that this fraction's not in lowest terms yet. How do we get in lowest terms? I find the prime factorization. So I happen to know the prime factorization of 24 is 2 times 2 times 2 times 3. And I happen to know the prime factorization of writing it in this order with the 2's first of 144 is 4 2's and 2 3's. And as you can see, I can do quite a bit of cancellation here. Every time I have a 2 in the top and the bottom, I'll write it again just so I don't overwrite the actual prime factorization. Every time I have a prime in the top and the bottom, I can cancel, 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 and the 3's cancel. And what I end up with is a 1 over 2 times 3, which is a 1 over 6. So 24 over 144 is a perfectly legitimate number. It's also the same number as 1 over 6. And even though I really like prime factorizations, this might be a place where you use a different type of factorization as you are getting comfortable with numbers. If you happen to know that 24 is 2 times 12, you might think about, can 44 be written as a number times 12? Right, so instead of boiling it all the way down to the primes, maybe you skip a couple steps. So again, that's the difference between a systematic approach that always works and maybe a faster approach that frequently works. And when it doesn't, you fall back on your other skills. All right. So there's verifying equivalent fractions. There's two other little topics in this section. I have to start that over. Verifying equivalent fractions. There's a rule in the book, but there's a much simpler way. And the reason it's a simpler way is because you all are building your skills with multiplication, etc. But still, when you get to big numbers, you're going to end up using a calculator, as would I. And this approach requires the use of a calculator. And as soon as you have a calculator, just find the decimal approximations or the decimal versions. And if they're the same, then the fractions are the same. All right, so let's look at minus 48 over 240 and 21 over negative 105. There's a rule where you can do some cross multiplying, etc., but just get the decimal versions of each of these. I think they're gonna be whole, well, they won't be whole numbers, but they'll be decimal versions. What's the decimal version of minus 48 over 240? I think it's negative 1/5 or negative 0.2, right?
It's negative 0.2.
I got it. Negative 0.2. And what's the decimal approximation of 21 divided by negative 105?
It's the same.
All right, so those fractions represent the same number. If you're gonna grab your calculator to do fancy work, might as well use your calculator to make it simple. And then there's an idea called designer fractions. Which is building an equivalent fraction with a specific denominator. If I have the fraction 9/5 and I want to turn it into a fraction that has a denominator of 35, I'm going to multiply by a special version of 1, which in this case is 7/7. Why did I choose 7? Because 5 times 7 gives me the 35. And I have to put a 7 on the top in order to keep it the same. So it's 63/35. So you build a designer fraction by multiplying by a special version of 1, which again is why I brought that up. We use special versions of 1 all the time, both for solving and for making specific fractions. All right, I'm going to stop the video.